everyone. Welcome to episode number 644 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. How about we shift left for this week's podcast? Certainly not an uncommon topic here on Fish Fry, but specifically this week, we're talking about how shifting left can enable innovation for software defined vehicles. My guests are Wensi Jin from MathWorks and Thomas Hülshorst from FEV. And we're talking about what is driving the demand for software defined vehicles today, the engineering challenges associated with SDVs, and why it is important to adopt a shift left mentality when it comes to software defined vehicle innovation. So, without further ado, please welcome Wensi and Thomas to Fish Fry. Hi, Wensi. Thank you so much for joining me.
Maria, thank you for having me here.
Absolutely. And hi, Thomas. Thank you for joining me.
It's my pleasure and my honor.
Excellent. Okay, so you guys, we're talking about software defined vehicles today. So, what do you think is driving demand for software defined vehicles?
Yeah, maybe let me answer first. So, being an engineering company globally active in this area with a car manufacturer, but also the supplier, I would say there are two different perspectives. So, one is more coming from a pressure to act. So, first of all, time to market is more and more shorter. So, there is accelerated development needed. We have a growing complexity, so more and more features are going into the vehicles, which are then at the same time also expected to be updatable, upgradable. And also, it is pretty challenging activity also to keep the development costs under control. So this is more or less a bit the pressure to act. What does that mean in more detail? First of all, we are used to have upgrades. So when we look at our mobile devices, so we can add new applications every second day or even every day. We are used to have updates of the operational system frequently. And more we expect something similar also from our vehicles so that we can add features maybe not even available when we bought the cars. At the same time, new features are enabled by this new architectures, which is, for example, using more data going into predictive services. So all of that is driving this. And again, at the end of the day, it's a combination of a market demand expecting such kind of features, and on the other side, also pressure to act to improve systems which are already growing over decades and became complex and hard to handle.
I absolutely agree with Thomas. One thing I would say is that I want to explain FEV and MathWorks. FEV has been using MathWorks tools for several decades, fairly long history using MathWorks tools. MathWorks, we build engineering tools. We really enjoy the relationship working with companies like FEV because they work with a lot of automotive companies in using the tools. And we certainly working with FEV, we also get to learn through a new interesting channel what industry is expecting. We work with automotive companies, but the deep relationship with FEV also brings us additional insight as well. So that's the basis for me to say I definitely agree with Thomas because of the trust and relationship we built over the last several decades. One other thing I would say is that the notion of software-defined vehicle, there is a vision to deliver that upgradable, updatable experience. I also think from a realistic point of view, this will probably will play out in several steps. Customers are in general expecting the software to be updatable in the vehicle, but perhaps it's starting from one end of the vehicle infotainment system. It's getting deeper over time. It's getting to, for example, the comfort convenience features. However, what's yet to come, what's being implemented, and that's what we're working with a lot of customers on, is making a lot of the deeply embedded features like battery management system, like the chassis control systems, make those features are also updatable. So the main point I want to make is software-defined vehicle is a journey. It will take several phases. We're only in the beginning part of this very exciting journey.
I love that, Wensi. All right. So let's talk about the industry wide engineering challenges associated with this demand.
There are many different challenges coming together. So let me start with more the view from engineering and technology. So we were used to develop features in a way that we put software on a controller to put the controller in the car, and then we had the feature. Now we have more generic platforms which can be used, and we need also to develop in a different manner because the software will continue to be developed. So we will add again features, we will update existing features, and we need a different kind of approach for the software architectures to make this happen, but at the same time also to the whole tool chain, the whole processes behind. So to have really this continuous development, integration, testing, deployment of such features. And that comes together then also with a changed set of tools we need to have in place. That's a main reason why we are in very strong contact also with partners like MathWorks. We use the tools for decades, and we need to change also these tools to these new setups, to these new boundary conditions. So virtual development, for example, virtual validation is a key here. So the so-called shift left. And exactly this is one of the main challenges. Another challenge is how the whole work is organized, the roles of a car manufacturer, the supplier, maybe a hardware supplier, software supplier. This is another challenge which also needs to be covered. So also to make sure that there's a clear setup of responsibilities at the end of the day that's pointing again in the same direction. The processes and the tools need to be in place also to make this happen so that all the different players can seamlessly work together and also to have a clear indication about the maturity and the quality of the product at the end of the day. So I would say these are, from my point of view, the main challenges. And just to add an aspect which maybe is also not to be neglected, when we talk about SDV, it's a very huge area. So I think essential is to really define what is the benefit I want to have for my specific car application. So what is the feature I want to add and what is needed to make the change? Because again, it's a kind of a step from a grown EE architecture I have developed over decades, which I know which is mature, which is also cost-wise under control. And now I need to change it. That brings another challenge to take the right decisions, how to make this step-by-step approach happening, and how to make this digestible in terms of time needed, in terms of budget needed. And also this is mainly supported by also tools, for example, in systems engineering, really to find out again what feature in the car has an impact on which element in the software, in the hardware, and how to do the testing again. So all of this comes together at the end of the day to make this, let's say, not only a hype, but really also a reality tomorrow, which is still digestible for the industry.
Yeah, maybe I'll add a couple of things what Thomas just said. FEV used MathWorks tools for quite a long history. So one thing we also say is that we both come from a system engineering background. We work with our customers, the vehicle manufacturers, suppliers, and so on, to look at system engineering. How do you develop a system? What's new here is software is now part of the system. Sometimes the software is the system. So that's a new way of thinking about the future SDV or mobility product. What that brings is oftentimes is that beyond the specific challenges Thomas mentioned, there's also the thing of a way of work. And how do we bring the system engineering expertise from automotive engineers who's already in place, delivering products, established track record, and the people who know how to develop complex software products together. So have these two sets of personas be able to collaborate together around the same framework. And that's something that's been driving MathWorks development for the last, I'll say, decade, because we see the trend coming. And what we're trying to do is link our traditional system engineering offering from a modeling, simulation, and system engineering practices with attributes that's required to support modern software engineering, such as the new software architecture, continuous integration, high degree of automation, virtualization. So today, I'm happy to say that we have a platform that serves the system engineering needs as well as the software engineering needs. And we believe such a platform is important to bring system engineering and software engineering together to collaborate together around the same framework.
All right. So, how is shift left an enabler for SDVs? And why is it important to adopt a shift left mentality?
So when we look at the shift left, fundamentally, right, we're talking about different benefits of, let's say, discovering problems early on in a very kind of common sense way. That common sense, that fundamental still holds true today, going into the software-defined vehicle era. The industry coined the term shift left to codify a set of way of work, best practices to do a lot of testing early on in the process. And what we really see is that the earlier you can discover the problem, you can resolve the problem right then and there. That prevents the problem propagate down the process, and you have to fix it later on. As we all know, a long delay in resolving the problem causes churn in the process, causes costly rework and things like that. So the shift left would enable you to do is instead of testing in the vehicle, you test in the bench. Instead of what you test in the bench, you test, let's say, in a simulation or early stage simulation to move these work verification as early as possible so that you can resolve the problem where the problem initially got introduced. That's actually more important today because the overall development process has been reducing, being compressed. And with software-defined vehicle, we always know it's a very complex product. Therefore, we have to find the best way to develop, to automate as much as possible. Now, automation is key, but automation itself doesn't resolve the problem of finding problems early on. So we need to have both methodologies. We need to have as much as possible in automation, but at every stage of the development, while you have an automated process to enable the engineers at that stage to discover problems, such as when you have early architecture design. What if you can simulate architecture and find out interface problems right then and there? If you have a new software feature, you can plug the software feature into a virtual vehicle to simulate the entire vehicle behavior along with the new software feature. So these are the ideas to support the notion of a shift left. So here I'm talking about the shift left itself, as well as the tooling and process that's needed to enable shift left.
I would like to add an aspect from engineering point of view. In the past, let's say we were used to have new features developed with a target on an embedded controller, for example. And it was still useful to have this first approaches for the model in the loop testing, software in the loop testing, and then we went to the hardware in the loop testing. So we had the different steps to be sure that everything is mature and bug-free before we go to the next steps. With these new architectures, it's even more challenging because instead of a target controller for a dedicated feature, you have a general platform, which is a central compute, which is then also replacing more or less an embedded controller with a more generic platform, and all the different capabilities even need more investigations very early in the process to be sure that also it will run not only on this target, but also it will fulfill, for example, functional safety requirements or real-time requirements, all of that. Even with the new architectures, it's getting more important than ever before to have this shift left approach. The software development will not stop with bringing the car to the dealer. It will continue even after the car is at the customer. This whole shift left is a must-have. It's not only to speed up and to improve efficiency and quality, it's even a mandatory aspect in the development to make this happen.
All right. So, what are the key strategies for implementation to make sure that we have a successful collaboration across teams?
So MathWorks, we're specialized in providing engineering tools to enable the developers of systems and the software features. So a couple of things come to my mind. So the first is that the collaboration needs to be supported by the environment. Collaboration is a spirit, but when it comes to engineering work, engineers use tools, development environments. So oftentimes, if you have very drastically different development environments, it's hard for teams to collaborate. So the first thing we think about from a tooling point of view is how do we provide a development environment for both software and system engineers to work together so that they can work in a consistent manner. That's the first thing. And that hugely influences how we shape our tools and how we kind of plan our work going forward. Second part is that also in the tools world, the tool chain needs to connect software and the system processes. And that's also to facilitate collaboration and also reduce rework. Imagine in a situation that you're making a software change or the software developer feels like a change needs to be made in a certain area. How would that person be able to assess the impact of that change? That person will have to look at the software feature, look at the whole software impact on the vehicle, software impact on other subsystems, and so on. So how do you establish a system where you can do this impact analysis by tracing up and down between the software feature and the larger vehicle design, right? So a tool chain to connecting software and system processes is hugely important. That's what we believe. The last part I would say is that nowadays the deployment of development tools usually involves not just engineering itself, is no longer individual in teams installing their own tools. In companies, IT, who's in charge of new development cloud environment, that's also very important. So there needs to be collaboration between engineering and IT. Here, I would say that tools certainly help. At the same time, we often find ourselves in the middle of working with engineering and IT to make sure that IT can deploy the tool in an optimal manner for engineering, or to make sure that the engineers chosen tool work well in the IT environment. So sometimes that also involves multi-party collaborations that we're playing a part to make sure that engineering and IT can work together.
From an engineering point of view, we work together with the car manufacturer, we work together with the tier ones, we work together with the ecosystem supplier. And this is also a challenge to bring together all of this different stakeholder and to make it clear about responsibilities, about how to guarantee that at the end of the day, the product is meeting the requirements. And I only can highlight what just Wensi mentioned. So the must-have is to have exactly this clearly defined processes and tool chains which are already guiding us, so that we even have a clear, dedicated role model about the different tasks to be done, represented exactly by this approach.
All right. So, can you share some real world examples where this shift left approach has been implemented successfully, specifically for software defined vehicle development?
I'll provide two examples, maybe two different flavors of examples, I would say. First example was a case study presented by Geely, a Chinese auto OEM. They presented at MathWorks Automotive Conference in China last year. So Geely has been on the journey to bring software development in-house. And as a part of that, they realized they need to automate development processes. However, what they also realized is that not only they have to automate, but they also have to find ways to test their software features, test the actual code as early as possible in the process. That's the shift left mentality. What they have chosen to implement is on top of the automation pipeline, they were able to integrate the use of models, because models is actually where the design gets captured for software features, and model is the source of the actual code running in the vehicle. They use automatic code generation for their software feature running in the vehicle itself. So their idea is, instead of testing the code, what if I test the model first? They were able to successfully integrate the idea of a model testing in their automation pipeline. So what they were able to do is, before they even started thinking about the code itself, they were able to test the design, test the architecture on the model level. And one benefit they reported is, by implementing this system, a highly automated testing system with a shift left concept embedded, they were able to root out a lot of the problems. What they reported is the first time integration success rate rose to about 90%, which is very much an improvement to what they had before. So that's one example. The second example I'll touch on lightly is that shift left is a journey the industry has been on. And Thomas mentioned the virtualization. The virtualization involves virtualizing many different things, virtualizing the software stack, virtualizing the hardware system, and virtualizing the processor. So many of these things are new to the automotive industry. And what we have been recently working on is working with the silicon companies to be able to connect the design process with a virtualization of the chip itself. One example that you saw at the recent MathWorks Automotive Conference in Detroit was that we co-presented with Qualcomm on taking a virtualized chip from Qualcomm to be able to run production-grade software on that chip. So that way, early on in the program, the software engineers may not have the real hardware to test it yet, maybe for a period of time. So during that time, they were able to use this virtualized chip to test the software, run the software against a virtual environment, a virtual vehicle, and to be able to gain speed, because they can get the software right before they have the first sample of the chip.
in the different areas of also electrification. So there was always exactly this challenge. So there was a new kind of powertrain established over the last years. And we, from the beginning, used also the MathWorks tools to do exactly this approach. So to develop everything already to the first models, to do the model in the loop testing, to go the next step to also simulate the processors, to do also software in the loop testing until we continue. So I would say this always was a very beneficial way, I need to say a mandatory way, to do such kind of development. So an example more in the SDV development is also using these new architectures. Some of the features are beneficial to be transferred to even a cloud application so that we have features which we used to be operated inside the car, but we have a more complex model even in the cloud to support this in-vehicle models. So even here, it's a new challenge where we need also to make this shift left happening. So for example, what we did is we worked on battery health and remaining useful life algorithms, which then were transferred to the cloud. So we had simplified models in the car to be sure that we always have a running version, even if the connection is not there. But in the cloud, we had the much more precise models. And to make this happen, again, shift left was the key. To make clear that all of this is working properly until we distribute it to the system. So this is one example where definitely also the SDV-enabled architecture is bringing not only another challenge, but also another opportunity.
Fantastic. Okay, so how has MathWorks partnerships enabled a more integrated engineering process, especially within this SDV ecosystem?
I would say when the first main focus was on more automated driving features, bringing more artificial intelligence into the systems, we already started again to intensify our discussion also with MathWorks, how we can, with our partnership, support these new trends. This is with the SDV going into the next dimension, where exactly this integrated engineering process is a must-have. So from the first feature definition, so what feature really I want to have in the car at the end of the day, and how to bring this into the different development steps up to really the mass production ready product. So this enables not only to be efficient, to be in time, but also simply to have a big reuse. So it's also important to mention when we do this systems engineering approach, there's a high demand also to get as much as possible reuse of existing assets, of existing artifacts already there. And this partnership with MathWorks definitely using the tools is also improving our performance at the end of the day in this regard.
Working with FEV has brought a lot of insight to our development, our engineering teams. So we're able to use that insight to further improve our products.
Fantastic. All right, you guys, it is time for your off the cuff question. So, Thomas and Wensi, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
I can answer that. Let me provide two bits of background because my answer is pretty basic. First, I travel a lot. So I'm actually in between two trips. I just came back from Germany and about to go to Asia. So at this moment, my special meal doesn't require a passport. I actually very much treasure a noodle in the nearby noodle shop close to my home in Ann Arbor, Michigan.
I love it. What about you, Thomas?
There are some similarities. I'm also frequently traveling the world. And honestly, that's a big benefit, exploring also different dishes in the different areas. So my choice today would also go in the direction of the noodles. So I love ramen, in particular the Japanese ramen. So that would be my choice today.
Excellent. That sounds wonderful across the board. Well, I think that's all I have time for today. Thank you so much for joining me.
Thank you for having us.
Thank you.
If you'd like more information about the topics covered in today's podcast, I've posted a slew of links below the player on this week's fish frying page on eejournal.com. And of course, in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is more your thing, you can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon too. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me, and our animated series called Libby's Lab. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on EE Journal. For the week of August 8th, 2025, I'm Amelia Dalton, and you've been fried.